When a line segment slices a circle in a way away from the center, there creates a segment. Check what this is here in Mathematics of Engineering. When a line segment passes from center to any point along the circumference, the line segment is called radius. Having two radii creates an arc, and the area bound is called sector. In case the line segment cuts the circle away from the center, the line segment is called a chord, and the area separated from the circle is called the segment. If the area of sector is computed through ratio and proportion, segment has a different approach, but equally easy. To take the segment, one has to figure out the area of the sector, and then taking away the triangle included, leaving the segment. Here are some examples to showcase the procedure. In the figure, chord AB subtends an angle of 130 degrees at center O. The radius of the circle is 8 centimeters, and we are to determine a series of parameters. First is the length of chord AB. Second is the area of sector OAB. Then, the area of triangle OAB, and lastly, the area of the minor segment as shown. First is the length of chord AB. If we drop a line from the center, perpendicular to chord AB, we bisect 130 degrees, and also create a right triangle, where by virtue of trigonometric functions, we can write sine of 65 degrees as AC all over 8. AC is then 8 times sine of 65 degrees, which is simplified as 7.25 cm. The chord AB is twice of AC, which is then 14.5 centimeters. Next is to determine the area of sector OAB. With sector, we use ratio and proportion. The area of sector OAB is to 130 degrees as pi times 8 squared all over 360 degrees. The area of sector OAB is then simplified as 208 over 9 pi, or 72.61 square centimeters. The next two requirements are the area of triangle OAB, which is half of base times height. From the circle, we can write the area as half of AB times OC. We still need to determine length OC, and again, from the right triangle, we take cosine of 65 degrees as equal to OC over 8. OC is then computed as 3.38 cm. The triangle is then solved as half of 14.5 times 3.38, which results to 24.505 square cm. Lastly, solve for the area of the segment as area of the sector less the area of the triangle. That is 72.61 minus 24.505, giving 48.105 square centimeters. The second example looks for the arc measure and the area of the segment of a circle with arc length of 8 cm and radius of 5 cm. First is to take the central angle theta through S as equal to r theta. Plug the given parameters to have 8 as equal to 5 theta. So theta is then solved as 1.6 radians. With the radius taken as hypotenuse, identify the other legs of the triangle after dropping a bisecting line from point O to point C. Through trigonometric functions, take sine of half of 1.6 as AC over 5. Distance AC comes out as 3.59 cm. Thus, the chord AB is then double of AC, that is 7.17 cm. For the other leg, use cosine of half of 1.6 radians as equal to OC over 5. OC is then computed as 3.58 cm. Now continue the procedure by solving sector OAB through ratio and proportion. That makes A sub S is to 1.6 as equal to pi times 5 squared all over 2 pi. The area of the sector is then 20 square centimeters. Next is to solve the area of the triangle included from half of B times H, or using the points in the circle, the area of the triangle is half of AB times OC, which is half of 7.17 times 3.58, giving the area of the triangle as 12.83 square cm. Finally, the area of the segment is computed from the difference of the sector and the triangle. That is 20 minus 12.83, resulting to 7.17 square cm. The third example provides a figure showing the cross-section of a cylindrical pipe with water lying in the bottom. First, focus on the maximum depth of water at 2 centimeters. If a line is reflected to the center, the length is the radius of 7 centimeters. So length OC is solved as 5 cm. With one leg of the triangle already identified, use trigonometric functions to solve for the central angle, that is cosine of half of theta as 5 all over 7. Half of theta is then computed as 0.775 radians. So theta is 1.55 radians. Also solve for the base of the triangle from sine of half of theta as equal to AC all over 7. That is sine of 0.775 as equal to AC over 7, where AC results to 4.898 cm. Thus, chord AB is 9.796 centimeters. With all angles and lengths already determined, we solve for the sector through ratio and proportion. We get A sub S is to 1.55 as pi times 7 squared is to 2 pi. The area of the sector is solved as 37.975 square cm. Next is the area of the triangle, which is half of base times height. That is half of AB times OC. These lengths have already been determined previously, so the area of the triangle is half of 9.796 times 5, resulting to 24.49 square cm. The segment is then solved as the area of the sector less the triangle, that is 37.975 minus 24.49, giving the area of the segment as 13.485 square centimeters. The next question is answered by taking the cross-sectional area multiplied by the length of the pipe. Thus, the volume of water is 13.485 times 30. The volume is then 404.55 cubic centimeters.